All right, good morning, everyone. How's everyone doing today?
Good, good. How about yourself?
Not too bad. All right, so today and tomorrow we're going to be talking about plate tectonics, which is the foundation of pretty much all modern geology. It's a relatively new theory um, compared to other theories like the principles of uniformitarianism and original horizontality that we talked about yesterday. This is one of the really newer ones just in the last century that we discovered this. But it's the foundation of everything that we study when it comes to hazards, really, because a lot of hazards come from plate tectonics, such as earthquakes, volcanic eruptions. Um, so it's a really important thing to study. So it's going to take today and tomorrow, but next week we're going to be getting into more actual hazards, starting with earthquakes, tsunamis, stuff like that. So we'll get into the more fun stuff next week. Almost done with the background info. So most of what we know about plate tectonics started with early map making. Just a couple of guys that were looking at maps and seeing how continents fit together, like Sir Francis Bacon. So he thought that South America and Africa kind of looked like they were puzzle pieces that they could be locked together. He didn't move any further than that. Francis Bacon was kind of just he was more of a diplomat than a scientist, so he didn't really move more into that theory. But that was one of the first instances where, after modern maps were starting to come about, we were looking at how continents fit kind of together. Fast forward to Edward Suess, who was an Austrian geologist. He studied a lot of fossils, specifically Glossopteris, which are these fossilized ferns, kind of fern-like trees, but their leaves were really well preserved in certain rocks. And he found them all over the southern hemisphere, from South America to South Africa, parts of Arabia, as well as India, and some in Australia as well. So he was starting to ask the question of why similar tree fossils would be found in such a wide-ranging area. Like, the area between South America and Africa is 3,000 miles. How could something be in one place and also 3,000 miles away? Completely similar with no seemingly different characteristics. So he theorized that there was some ancient supercontinent called Gondwana, which was a combination of Africa, South America, India, Australia, and Antarctica. They were all smushed together at one point, and for some reason, they're not today. So he wasn't able to fully develop that, but he thought that the supercontinent idea was a good starting point, that there were at least some connections that flowering trees such as this could at least pollinate and repopulate in different areas, and then those different areas spread apart after those populations of trees were already there. So now we get to the rock star, Alfred Wegener, who was he wasn't a geologist. He started out as a climatologist. He was really interested in studying past climates, so that kind of got him into geology. Um, he actually was the first person to use weather balloons, and we still use weather balloons today because of how the data that we get from them is incredibly it's a high quality data, and they're also incredibly inexpensive. A weather balloon doesn't cost much, and it's an incredibly useful scientific instrument to monitor weather patterns. So he was also in World War I, and then he worked as a weather forecaster. During this time, weather forecasting was incredibly difficult just because we didn't develop radar yet. So weather forecasting was an incredibly hard job. But he was really interested in polar climates. He worked in Greenland for a bit. He worked in the poles, both Antarctica and the Arctic. And he also traveled to Greenland a number of times, at least four that we know of, until his last one in 1930, where he went missing. So he was really interested in what Edward Suess was looking at in those fern fossils that he found all over the southern hemisphere. The reason that that theory didn't take off was because of the idea that, oh, seeds could travel and pollination can travel by wind. So most people were like, okay, as far-fetched as it is, maybe, just maybe, something carried those seeds and pollen that far enough over these areas in the Atlantic. So it's not until Wegener starts discovering animal fossils in different parts of the continent. So Lystrosaurus, which is this reptile, little bit larger than a pig. How could this herbivorous animal be found in different continents? It would have to walk. It can't swim. It has to walk to these areas. So then people thought, oh, maybe island hopping, maybe there were some land bridges between them at some point before the sea level rose for some reason. And then he found some even more from Africa and South America. Mesosaurus, which is fully aquatic, but it lived in fresh water. So if it lives in fresh water, it's not going to travel by the ocean. So this was a pretty significant finding for him that he continued to work on it. So these were the biggest hypotheses at the time. Rafting, which is like some driftwood or just debris in general that plants or animals can just latch upon to travel with currents to different continents. Pretty unlikely for animals, but maybe more likely for plants and such. We have Isthmian links, which are just these land bridges that connect continents. You've probably heard of the Bering Sea land bridge between Alaska and Russia, which is where modern humans came all the way through Siberia, through Alaska, and then populated the Americas. Also, the idea that these long island arcs were able to be traversed, or they could swim across them close enough that they could just kind of hop to these islands until they get to a continent during periods of low sea level. But these were just ideas. They weren't testable. So there was really no way of knowing. So Wegener was the first person to suggest a supercontinent, a huge supercontinent of Pangaea, where all of these continents were smushed together, thus giving the land access for all of these different species that we see in the fossil record to just traverse wherever they want. And then those populations establish in these different areas, they die out, their remains get buried, and then they enter the fossil record. After they're in the fossil record, the continents start to rift apart, and then anything that evolves after that starts to evolve separately from its ancestors that were once joined up. So his evidence was there's a lot of glacial deposits in equatorial regions like Africa, parts of South America, India even, and of course Australia as well. Why would these glacial deposits be in such warm and humid areas? It makes no sense unless those continents were smushed together and pushed southward or north, so far northward that it would have a cold enough climate to form these massive glaciers and generate these glacial deposits. So the first hypothesis was that there was global cooling during the Permian, which is for some part true, mainly because the end Permian was one of those extinction events that we talked about yesterday. a lot of uh, dying off of certain species, mainly due to the lack of um, herbivorous food for them. But he also has warm tropical swamps in the north. So if there was global cooling, why would we have these really warm tropical swamps in this area, but not in other areas? So that means there had to be some sort of shift towards one of the poles or the other. Mainly that the northern hemisphere, America, Europe, Asia, was more southward towards the equator, while all those in the southern hemisphere, South America, Africa, India, were closer to the South Pole, giving them a lot cooler of a climate. So this is where the theory of continental drift comes about. So this was the precursor to plate tectonics, the idea that the continents are kind of floating on the surface of Earth, not in the ocean, but the continents are, for some reason, they're independent of one another, and they can separate and they can come together throughout geologic time. So this was helping to explain certain ages of certain mountain ranges. The Appalachian Mountains are kind of lined up with the Pyrenees and the Atlas Mountains over across the Atlantic, as well as the Caledonians in Scandinavia and parts of Greenland. If they were once part of a continuous range and then separated, they would of course be of the same rock type and same age and same structure. Fun fact, if any of you have ever tried to hike the entire Appalachian Trail, there's a continuous trail that goes from the southern part of the Appalachians in America, goes all the way up to Canada through Greenland, and then you come around and go south through Scandinavia and end in Africa. It's called the Geologic Appalachian Trail. So if you're ever super into through hiking, try it out. It seems like it's a cool thing. So this is what Pangaea looked like around 250 million years ago. As you can see, Africa and South America are that puzzle piece that kind of started the whole theory. America smushed up against Africa as well as Europe. Asia is up closer to the North Pole. Southeast Asia is its own continent at the moment, but it's like on its way for a collision course. India is smushed up against Africa at the moment, hasn't gone on its course towards Asia to form the Himalayas. So all of these southern hemisphere areas are very far south, and they're getting a lot more cooler air, a lot cooler of a climate. So life on Earth is probably migrating northwards towards North Africa, North America, and Asia to get to a warmer climate on the equator. So the initial response to Wegener's paper was not great. A lot of American geologists didn't agree with it, mainly because Wegener was a climatologist. He wasn't a geologist. And that was back when scientists were really rooted in their field, and they really didn't have much leeway and deviation from that. And there wasn't a mechanism to explain how the continents moved. It's great that everything lined up, that the continents could be moved together, and they were at one point smushed together in a supercontinent, and the fossil record matches that. But unless you can explain how they rifted apart and how they came together, there's really not much leeway in understanding that. Most of his evidence was also from the Southern Hemisphere, not from the US. So a lot of geographical issues when it comes to this. So obviously, American geologists have a bit of a bias because they understand a little more about the Northern Hemisphere. And then the bane of all scientists, as I'm sure you're experiencing with me lecturing this class, Wegener is a very boring speaker. And a lot of presentation when it comes to presenting new scientific ideas, you have to be a little more charismatic, I'll say. So fast forward let's see, he disappeared in 30, about 20. So 20 years into the future. We're in the 1950s now. We're after World War II, we're developing new technologies. We have sonar and radar, which were used in submarines. And now we're starting to use these for science. So Harry Hess was a naval officer. He worked for the Office of Naval Research. He fought in World War II, and he also was a geologist who was really interested in studying the seafloor. So they used sonar waves to find submarines because they can't see them on the surface. So you send out basically a ping of sound, and based on where you get a reflection, you have a location of some object. And based on the reflections of those objects, you can tell how large or small that is. So he had the idea of let's point it just straight down to the bottom of the ocean, and let's just measure the time that it takes to for that reflection to return. So starting at one continent and just in a straight line to the other continent, in the Atlantic, he just did this sonar survey, and you can see this profile at the bottom of the screen here. So you'll notice that rather than what they expected, which was just a trough, there's a mountain range in the middle of the ocean. And this was incredibly surprising to everyone. Nobody expected some huge feature like this in the middle of the ocean. If anything, there'd be more water weight at the center. So you'd think that things would be a little more weathered down and smushed, but no, it's a whole mountain range. So using that data, two geophysicists and, well, a geophysicist and an oceanographer, Marie Tharp was an oceanographer, and she was a map maker. They made this map of the ocean floor, the first bathymetric map of the entire world ocean. So if you look at this map, you'll see a couple of features. Number one, the Mid-Atlantic Ridge running right down the center of the Atlantic. You also have these ridges in the Eastern Pacific and going down through Antarctica, coming up below Australia. There's some ridges in the Indian Ocean, and they all seem to linearly connect. So this entire map really changed our understanding of what geology is, because this was the first time that, number one, that we've ever mapped the seafloor, and number two, that we've seen such distinct new geologic features. So the thing that was the most surprising is that if these mid-ocean ridges are mountains, why don't they have peaks? They have rifts, not peaks. So we see these fractures, and if you look on the image on the right, we see these discontinuities, these faults. So like something's being pulled apart. Something else that we discovered was we did some magnetic surveys. Basically, you tow a magnetometer across the sea floor and you record if you get a peak in magnetism or if there's less magnetism. And we noticed that along the axis, perpendicular to the axis of the ridge, we were getting some pretty regular reversals in magnetism. You would get a period of magnetism that would drop, and that would continue along the ridge axis pretty standardly. So we're getting a lot more evidence here. So why do we have these reverses in magnetism? Earth's magnetosphere switches periodically, which is crazy to think about, that at some point in the past, you would be looking at your compass and it would be pointing north, and all of a sudden it would spin around 180 degrees. We don't know why this happens entirely yet, but this has happened in our full Earth's history that we can measure. It's probably happened 183 times, where the magnetic north has just flipped to magnetic south. Now, it's not like geographic north, it's magnetic north, where just the pole reverses and the magnetic pole is pulling towards the geographic south rather than geographic north. So these reversals are recorded in these rocks because magnetic metals in rocks want to align with magnetic fields. So if we have rocks that are aligning to the north, and then all of a sudden in a new segment right next to it, they're aligning to the south, that's where we can map out a pole reversal. So this happens whenever we get new rocks that are crystallizing. So whenever we have a lava flow, lava flows have a lot of iron in them because they're coming from the center of the earth. Bring up iron, magnetite, all these metals that are heavily susceptible to magnetic fields. So as it's crystallizing, at first it's all kind of wacky, but the magnetosphere kind of aligns all of these dipoles within the rock itself. So this magnetic alignment is reflective of the time period that the rock forms. So if we're, for example, Kilauea is erupting right now, all those rocks that are crystallizing, they're aligning with magnetic north right now. So whenever thousands and thousands of years in the future, they look at Kilauea's rocks, they're going to reflect the same magnetic pole that we have today. If we look further back on Kilauea, we may see something different. If we go back at least 1 million years, we may see it pointing to the South Pole, which is really interesting and useful. So whenever we were looking at these seafloor maps and we were looking at these magnetic reversals, we see that they're parallel to these mid-ocean ridges. So as we go out from the ridge, we see periods where it's the same and where it's normal polarity, then reverse, then normal, then reverse, and it's symmetrical across both directions from the mid-ocean ridge. So this is all recording paleomagnetism, old magnetic reversals that have happened in Earth's history. So this is useful information to have. So as new crust is forming, as the crust is rifting apart and new crust is formed in those rift zones, we're going to get those linings of magnetization, and we can also help age date these different formations on the southern parts of on the bottoms of the seafloor. So we get newer crust, obviously, at the ridges where all that fresh magma is coming out. And then almost in perfect symmetry, you get older crust with distance from the ridge itself. So if we know the ages and the distance from the ridge itself, we can establish a spreading rate. And this can help us know how much time has passed in between the seafloor spreading. And if we know how fast the seafloor is spreading, we know how fast the continents themselves are moving. So this is a pretty popular map of the ocean floor. This is showing spreading rates. So if you'll notice, the gray parts, if you let your eyes adjust to it, the gray parts of the continents, right in the center, you have North and South America. The red on this map is significantly younger rocks. So from 0 to 9.7 million years. The blue is the older rocks, 180 million years. So you'll notice that all the younger rocks follow that ridge down the center of the Atlantic. They also follow the other ridges in the Southern Oceans, the ridge in the Indian Ocean, and that ridge that's in the Pacific. And almost perfectly symmetrically, it increases in age as you go from these ridges. So this is going to be really useful in establishing how old these continental motions are. Something else that we're learning is that hotspot locations also leave trails that show plate motion. So Hawaii, for example, is a hotspot. And then right now, Hawaii is just pouring magma out because there's this very localized ball of magma beneath the crust. So if you think that that hotspot is staying still, and the crust is moving on top of it. So it's just going to leave a bunch of islands in a line following that crustal motion. So if we look at all of these island chains in the Pacific, it's telling us a general trend of the plate direction. All of these lines are pretty much parallel. The one thing we haven't figured out yet is why there's a bend in the shape. At some point, that plate motion just shifted to a different direction. So now we know that the continents move. Why are they moving? What's causing the motion, and what's the engine for that tectonic movement? So first, we have to know a lot about the characteristics of the Earth, specifically its density, the volume, and the size of the Earth. So Eratosthenes was the first person to calculate the circumference of the Earth. He was a Greek philosopher, and he noticed that in these two Egyptian cities, Egyptian cities had these large obelisks, looked just like the Washington Monument, and he noticed they cast a shadow at a certain period of the day. And he realized that at the same period of the day, they were casting a different length of a shadow. So using this knowledge, he figured out that the Earth was a curved surface long before we were able to figure out that Earth was not flat. So this Greek philosopher figured that out. He figured out the angle, he figured out the calculation required, and he came up with the first measurement of the radius of the Earth in 200 BC, which is nuts. That's crazy. Fast forward about 1800 years, you get Isaac Newton, and he looked at how mass relates to gravity and how larger masses increase gravity. So we're all acting upon Earth's gravity, and Earth's gravity is acting upon us. Because Earth is much larger, Earth is acting upon us a lot more than we're acting upon it. So if we know Earth's mass and its volume, we can calculate Earth's density. And the pretty average and accepted value is 5.42 grams per cubic centimeter. But this doesn't match the rocks that we have on the Earth's crust. Granite, which we find in a lot of our mountains, is 2.7 grams per cubic centimeter. Basalt, which makes up a lot of the oceanic crust, that's a little denser, but still not as dense as the overall density. So we're missing something, and most likely what we're missing is the stuff on the center of the Earth. There's stuff at the center of the Earth that has to be a lot more dense, that brings up that average density that we're not able to reach yet. So the reason we know a little bit about what's at the center of the Earth is early studies provided some examples of ophiolites. Ophiolites are these segments of rock that are pushed up from the mantle into the surface, up onto the crust. And basically they're mantle rocks that have never seen the Earth's surface, so they're really unstable, so they weather and break down really fast because they're so used to high temperatures and high pressures closer to the center of the Earth. But some of these have persisted, and we can see them like right in the Caribbean plate around Puerto Rico. And whenever we dredge, we're able to pick up some of these rocks and sample them and calculate their density. And we find that they're a lot denser than the stuff on the surface, which makes sense. Denser things are heavier, they're going to sink further to the center.
Could you go back a slide real quick?
Was that a question?
Yes, please. Could you go back a slide real quick? I just didn't get the rest of the Earth's density.
Oh yeah, sure. This one?
Yes, thank you.
Yeah, no problem.
Thank you, that's it. Thank you.
All right. Yeah, if I'm going too fast, let me know. All right, so we've seen this before in our Earth materials lecture, the chemical composition of the crust. The heaviest elements here are magnesium and iron, but they only make up around 8.1% of the Earth's crust. Everything else on here is very, very light. If you look at the periodic table, oxygen is in that first row, silicon is right next to it, potassium, sodium, calcium, they're all up there in terms of weight. They're not heavy at all. But magnesium and iron, very, very different. So people started to think, oh, let's start looking at magnesium and iron. Maybe if we're finding it on the Earth's surface, it has to be found somewhere. So whenever we do get rocks from the interior, this is what we're getting. We're getting peridote and we're getting olivine and pyroxene. Both of these are heavy in magnesium and iron and a little bit of silicon. So because it's so enriched in magnesium, these are ultramafic rocks. Remember we talked about felsic rocks, mafic rocks. These are what's known as ultramafic rocks, meaning so much magnesium, so much iron, and that makes them so much denser and heavier than the other minerals. Felsic minerals, which make up the continents, they're much lighter. They have a lot of silicon in them. So they tend to float towards the surface of the Earth. That's why the continents are so high, whereas you get your mafic rocks, the basalts, that sink to the bottom, which is why they make up so much of the bottom of the ocean. Then you get your ultramafic rocks, your olivines, your pyroxenes, which make up the center of the Earth. So we're going from light, heavy to heaviest. So a prevailing theory as to why we have iron and nickel on this planet is because whenever during the Hadean eon, long ago, 4.6 billion years ago, Earth was getting bombarded with meteorites and asteroids. And asteroids are mainly made of iron and nickel. This is the Hoba meteorite, and it's found in Namibia. It's 60 tons. It's the largest piece of meteorite that we've found on Earth's surface. All the other meteorites that were from like the meteorite that wiped out the dinosaurs, the one that started the Siberian traps, we can't access those. They're at the bottom of the ocean and they're mostly destroyed, just spreading their chemical composition everywhere. But this one has persisted at least. So we're able to measure it and we're able to take samples of it. So we know it's composed mostly of iron and nickel. So if this is a rock that came from space, that we know that most of the rocks that are bombarding Earth are abundant in iron and nickel, and those rocks are abundant in our solar system. So if Earth was created from this accretion of all of these asteroid impacts that just conglomerated due to gravity, that means most likely the center of the Earth is most likely made of iron and nickel. And this is going to help average out our density of the Earth. If we have the lighter stuff, the granite, the basalt with roughly 3.0 grams per cubic centimeter, iron is 8 grams per centimeter, nickel is 8.9. So these are a lot heavier. This is going to help average out the stuff that we're missing. So how do we get to the Earth's interior? We can't. I don't know if any of you have seen the movie The Core. It's a terrible movie. It's very scientifically inaccurate. I would not recommend it. Also, the acting is terrible. But the idea that we can enter the core is, or enter even past the crust is, it's not happening. If you imagine as you're drilling a hole through the Earth's crust, the pressure that those rocks are experiencing just increases with depth because there's more and more weight on top of it. So the deeper you go, the higher the pressure. If you create a void space, those rocks are going to slip and they're just going to break your drill bit. So we can't get very deep, and we can't even reinforce the borehole as we go, just because there's not enough time or energy or money to make that happen. So one of the places that we've drilled the deepest is in South Africa. It's a very, very deep gold mine, and it has a lot of depths. But if you get down to those deeper parts and you touch the walls, they're about 60 degrees Celsius. So they're pretty hot. It'll hurt your hand if you keep it on there for a while. Then there's an even deeper borehole in Russia, which is 12.3 kilometers. We are still not penetrating the crust. The crust is about 15 kilometers, so we haven't even gotten there yet. So we're not even into the stuff that's deeper into the center. Temperatures at that one are even higher at 180 degrees C. So that's very hot. So how do we know about Earth's interior? Well, we're measuring earthquakes. So Andrija Mohorovic, who I just butchered his name, but he's a Croatian seismologist. He studied earthquakes. Croatia gets a lot of earthquakes because they have a lot of fault systems. So he was able to measure seismic waves whenever we finally developed seismographs. So he was measuring the speed of those waves from the source to the seismograph, and he noticed that at a certain depth, those seismic waves increased in their velocity. So those waves were able to arrive first if they went down into the deeper mantle, traveled in the deeper mantle for a bit, and then came back up. So that tells us that whatever the mantle is made of, seismic waves preferentially will travel through it faster than the stuff on the crust. So because he was the one to discover this boundary, that's why we call it the Moho boundary, which is the boundary between the crust and the mantle. We know that this change in density, which is what defines that seismic velocity, that's where this difference in composition is. So I'm not going to go into too much detail about seismic waves because we're going to talk about that next week when we talk about earthquakes. But we know whenever an earthquake occurs, seismic waves travel outward in all directions. And they're going to travel through the earth as well. So they'll travel outward through the mantle. Some of them might even enter the liquid outer core, the solid inner core, and then on their way out. So we can measure those differences in velocity through those layers whenever it comes out to the other side. And then we can calculate an average velocity of those materials in the center of the earth. So if you look at the graph on the right, you'll notice that depth is decreasing along the y-axis. Along the x-axis, velocity is increasing to the right. You'll notice that velocities increase as you go through each of these transition zones into the mantle. And then you'll notice that those velocities drop off in the outer core. Can anyone think of a reason why we would drop off in our velocities in the outer core? You can just throw out any guess that you want. Nobody has a guess?
Is it because it would be very hard to transmit a force through a liquid since the
That's
outer core is a
exactly
liquid?
right. So if you imagine imagine pushing water. Like you're at a pool, you're pushing water. So you can do it this way, but imagine taking your hand onto the surface of the water and just trying to push it that way. That's kind of what we're dealing with when it comes to seismic waves in the liquid outer core. It can't transmit those seismic waves very well. So you see a drop in the velocity of P waves, even though there's still some velocity because the P wave is a compressional wave. It can at least still transmit through. S waves cannot transmit through it at all. So the overall velocity drops until you get to the inner core, which is solid, and then they can transmit through again. So very good, Adam. And we're going to talk about those next week. That'll be really important. So this is a basic structure of the Earth. So we have the crust, real thin outer layer, the mantle, which At the top, it's more solid, and then it gets a little, not liquid, but a little more malleable. And then we get to the outer core, which is just liquid rotating around the dense inner core, which is just iron and nickel, pure iron and nickel. So the crust has a lower density, as you can imagine, since it's on top. All of the lighter things of lighter chemical compositions, they want to go up because they have a lower density. So you have continental rocks, which are your granites that form mountains. They're all the way up here. Oceanic crusts, which are made of basalt, so they're a little lower because they have a little higher density, but they're still not as dense as mantle rocks, which are just much higher density. Your pyroxenes, your olivines have a lot more magnesium. And then you get to your core, iron and nickel, which is as dense as you can get. I have a piece of, it's a siderite, which is just a piece of iron, which maybe I'll bring that into class if we go in person next week. You can hand it around, see just how dense iron rock is. But yeah, so based on these different compositions, we get differences in density that we can map out using these seismic waves. So each of these layers is a little more complicated and complex. So this is why we're going to use the Oreo cookie model. If you imagine an Oreo cookie, you have the hard and brittle actual cookie portion, and then you have this creamy filling, which is, it's not a liquid, but it's softer than the cookie. So at the crust and mantle boundary, you have what's known as the lithosphere, which makes up these tectonic plates. They're different in their densities, but they're both moving as a unit because of their brittleness and their thickness. And they're floating on top of this somewhat softer rock, which is known as the asthenosphere, which is the greater part of the mantle, and it's deeper. So it's a little more liquid, a little more able to flow, but it's still solid rocks in there. And then we get to the lower mantle, which is a lot harder rocks. Even though it's hotter down here, you'd think it would melt. We find that the pressures are actually so great that they're able to stay a lot harder. So that's where we're getting this these physical characteristics of the hard upper layers and the more softer asthenosphere. So the lithosphere, the important things to take away from this is the lithosphere is what makes up our continental plates and continental crusts and oceanic crusts, and the asthenosphere is what those crusts float on top of. So the Earth isn't a perfect sphere. We've got a lot of different structures on top of it. So as you can imagine, the thickness of the crust is going to be different all over the world. So if you look at this map where the depth to the moho, which is the depth to the mantle, remember, red is thicker, blue is thinner. So it kind of makes sense to see the thicker portions where we see them. So that big blotch in the middle of China and northern India, that's obviously the Himalayas. It's a very, very thick portion of the crust. It's also part of Tibet. Tibet, interestingly enough, may become its own craton at some point, which will be pretty cool. Also in South America, you can see the Andes Mountains, some of the highest mountains in the world. That's also going to be a portion of very, very thick crust. And then all of the blue where all of the oceans are, that's obviously going to be the thinner crust because you have a lot denser materials in the oceanic crust. You get your basalts, which are heavier, so that you're going to get a lot thinner crust. Keep in mind as you're looking at this, those blues don't make it all the way to the coastline. The coastline doesn't just drop off. So there's this thing known as the continental shelf, which extends outward a few dozen miles, and then you get that drop off into the oceanic crust. So keep that in mind. So we mentioned this before, but the main differences in our crust are oceanic and continental. Our continental crusts are less dense, which is why they're able to stay above water. They build up above the water, and they're able to build up much higher and thicker. They have a greater total mass and a greater area, and they contain some of the oldest rocks in the world because they're able to stay stable on the surface. They're not entering back into the earth, whereas oceanic crust is a lot more dense. Obviously, as we saw on the last slide, it's a lot thinner, and they tend to be younger, tend to be newly formed from those rift zones in the middle of the ocean. Tell you what, let's take a 10-minute break here, because that's a lot of information to throw at you guys. So I'll 10-minute break, and I'll see you guys back at 11. All right, guys. Hopefully you're all back. Only have maybe 20 more slides, and we'll be halfway through plate tectonics, and then we'll pick it up tomorrow. Let's screen. Okay, so we'd already discussed the lithosphere and the asthenosphere. Think of that Oreo cookie example. Lithosphere is the top cookie. The asthenosphere is that softer filling. So the lithosphere is floating on top of the asthenosphere. And this is a principle of what's known as isostasy, which is the idea of exerting weight on top of a solid or semi-solid. And it's similar to what Archimedes studied when he studied buoyancy, or whether if you put something in a liquid or immerse something in a liquid, everything that is displaced is equal to the mass of that whatever object you put into it. So isostasy is similar. If you are putting a slab of lithosphere on top of something in the asthenosphere, a heavier object is going to exert a greater force onto that asthenosphere than a lighter object. So it's going to displace the asthenosphere outward. And this is what we see at the boundaries of the continents and oceans. So continents have a lot greater mass, a lot greater area. Obviously, you have all that weight of the rock on top. Even though it's a lighter rock, there's a lot more of it, so it has a greater mass. So it's sinking and it's exerting a greater weight onto the asthenosphere and into the mantle. Whereas the oceans do not exert that kind of weight onto the mantle. So continental crust kind of rides the asthenosphere at a much greater depth, and you'll see a lot more of this like bulging effect right at the margins of continents rather than in the middle of the ocean. What is this doing here? This would have been helpful earlier. All right, well, we'll go with it. This will be useful in explaining how earthquakes work. But whenever we're talking about the liquid, whenever we were talking about the liquid outer core and the solid inner core, the P wave direction, each earthquake has a P wave and an S wave, which is the primary wave and a secondary wave. This P wave model on top, it's a compressional wave. So it's pushing everything in front of it. So if you imagine pushing, as we talked about, if you're in the pool and you're pushing water, you can do that. We're able to push and compress fluids. That's why hydraulics work. Hydraulics are just cylinders of liquid with when we push them and it exerts greater force. So we're able to exert a P wave motion onto liquids. S waves cannot. S waves are more of a what is that? An oscillation, a shear rather than a push. So we can't shear a liquid, but we can push a liquid. So this is why we're able to map out the outer core and the inner core and see the differences between them. All right, so basically this is our candy corn model of the layers of the Earth, which I'm sure you guys have seen before, but this is a little bit more in depth as in terms of breaking them down. So again, we have the lithosphere, which is rigid. It's much lighter. It's made of silicates, and it's much more brittle, so it'll break and it'll fault and it'll collapse in certain places. But that's what we live on. We live on the lithosphere. We get down to the asthenosphere, which is a portion of the Earth's upper mantle. It's a solid, but we use the term plastic. Plastic is a solid that flows. So like a glacier is kind of a plastic because it's a solid sheet of ice, but it kind of morphs into shapes based on, and it kind of fills the voids. So it's a little more fluid, not as rigid. Then we get to the mesosphere, which is the rigid portion between the upper mantle and the core. So we're at the bottom edge of that Oreo cookie. We're at the more brittle and rigid part. Then we're getting to the core itself. The outer core is completely liquid. We're not talking plastic, we're talking fully liquid. Here, even though there's a lot greater pressure, there's enough heat to create and melt everything that's at this outer core portion. So it's completely liquid and it's flowing around the solid inner core, which is completely solid due to the pressures. And that liquid outer core, solid inner core interaction, that dynamo that's created from it by the liquid core flowing around it, that friction is what creates our magnetosphere. That magnetosphere is protecting all life on Earth from a lot of UV rays, cosmic dust. So that's a very useful thing to have in terms of a planet. What is this doing in here? This should not be in here. All right. So this video will be a lot more useful to have the sound to. So I'm going to recommend that you guys look at this on your own time whenever I post the lecture slide. But this is kind of introducing the idea of convection. So we asked the question of what is driving plate motion. Since we know what the structure of the Earth is, what's going on in those layers that's causing the plates to move. So a lava lamp is a very good example. Convection is a heat transfer where heat is transported by different parts of matter. So if you imagine plumes of magma being brought up to the surface, that's going to bring heat, and that heat is going to drive plates to subduct under each other. So lava lamp is a great example of this. Basically, when it comes to convection, you have these cycles, these cyclic motions. So you have portions of the upper mantle that are bringing in up a lot of hot material up to those mid-ocean ridges, up to hot spots. That creates this motion coming up, and then as that disperses through the crust, it's going to spread out and it's going to pull the plates apart at spreading centers. And that motion is going to continue along the edge of the plate. So if you look This looks like South America on the left, Africa on the right. We're pulling those two apart from the mid-ocean ridge. Once we get to the other side of the plate, you can see in this gray, this is part of the existing plate. It's being pulled down from those convective forces, and it's subducting. We call this subduction. It's subducting underneath another plate. This is where we get trenches. This is where in different areas we also get mountain building, but it's pulling that plate downward back into the mantle. And that rock is going to eventually melt down. It's going to mix in with the other mantle, and it's going to repeat the rock cycle again. It's going to end up coming back up into the mid-ocean ridges, and then it's going to expel and then become another brand new igneous rock. All right, so just type your answer into the chat. Which of these layers is completely liquid? All right, very good. You guys seem to get it. Outer core, well done. So where is the Earth's crust the thickest? Based on this, this map here. Very good. And that makes sense, right? That's the Himalayas, that's the Tibetan Plateau. That's not only is it the highest place on Earth, it's also where we have all that continental crust built up in between us and the mantle. So well done, guys. Whoa. Oh, I'm so sorry. I thought that said thickest. Sorry about that. But thank you for listening to instructions. Well done. So what we know about mid-ocean ridges, as well as plate boundaries, are they're volcanically active. So all along the mid-Atlantic ridge, we're expelling magma, and that in itself indicates volcanic activity, right? It's not violent. It's more akin to what we see in Hawaii, where it's just these gentle lava flows coming up from the mantle. These are the way these work is that you have these two ridges right here, and you have new magma coming up. It hits that ocean water, it solidifies, it cools down, and then eventually that plate motion is going to break it apart and move it. And then you're going to get new magma coming up, cools down again, breaks apart and moves, and you get that motion ongoing, that constant cycle of cooling, breaking, and moving. So whenever we get new volcanoes, new volcanic action at mid-ocean ridges, most of the magma is even cooled before it even gets to the surface. So we get these like kind of igneous intrusions that enter into the surrounding plate, into these like dikes that go up into the plate itself. The other 25% we get these beautiful like pillow lavas that you see here in this video. This is what a volcanic eruption at the bottom of the ocean looks like. And you can see this all along the mid-ocean ridge. And because it's so active, this is mostly 80% of all of Earth's volcanism, almost all of it. Some chemosynthetic organisms have attached themselves to these areas because they feed on things like sulfur. So these are like perfect environments for them because they can feed on all those volcanic gases that enter the ocean water. So just to reiterate, whenever we get these mid-ocean ridges, you can see that rising material is pushing up that portion of the plate due to all of that heat and that energy. That's why we have those ridges and those peaks, but then they're going to rift apart due to the convective cell. And this is why these are known as spreading centers, or what's also known as divergent plate boundaries. So we have a number of different plate boundaries. Whenever we have a mid-ocean ridge or something similar where stuff is spreading apart, that means they're diverging, they're coming apart. What does that look like on the land though? So if you'll notice, Iceland is actually an island that's situated right on top of the mid-Atlantic ridge. So it's shallow enough that all of that magma that's coming up to the surface and expelling into the ocean is able to build up an island. So Iceland is a very active island volcanically. It's had a lot of volcanic eruptions in the past, some pretty violent. I don't know, some of you might remember a while ago there was an Icelandic volcano called Eyjafjallajökull, which erupted and sent this huge ash cloud up into the stratosphere, and it grounded planes from everywhere in Europe for probably 2 to 3 weeks. So it was pretty damaging economically, but not in terms of deaths at least. But this is what Iceland's surface looks like. So this picture at the bottom left, this is the diverging boundary between two continental plates, the European plate, the Eurasian plate and the North American plate. So we get this rifting here, and you can actually go to this place and stand in between two tectonic plates in Iceland, which is pretty cool. But because we have this rifting on the surface, you're creating a void space for, this is where we get into the geomorphology. All this sediment starts to infill, and as it's pulled apart even more, more sediment may come in, more water may come in. This is what it looks like just off the coast of Iceland to the right. These are the two rocky tectonic plates, and you can dive in between them, which is on my bucket list because that seems like a pretty cool thing to do. There are also areas where we have more divergent plate boundaries. East Africa is one of them. The East African Rift is this huge rift system between the African plate, the Somali plate, which are two minor plates. They make up the greater African plate. But this rifting has been pretty steady, probably about 2.3, ranging from 1.5 to about 5.2 millimeters per year. So that's pretty hefty rifting. That's a little faster than how your fingernails grow. It's about how fast your fingernails grow. But what this rifting has done is it's created all these different geologic features that we can see on the surface. Like Lake Victoria wouldn't exist if it wasn't for the Great East African Rift Basin. So whenever you create all of those pulling aparts in that void space, you create these sinks, these basins where sediment and water can infill. So this is ongoing in East Africa. It's one of the most interesting places in the world to study tectonics, just because of it's on the surface, so you can see the rifting happen. You can do a lot more measurements just because it's on the surface. Putting scientific instruments on the bottom of the ocean is very expensive, very difficult as well. But you can put so many seismographs, you can put so many instruments just on top of the surface here, which makes it a lot easier for scientific study. So subduction zones are basically the end all of the convection cell. So the whole cycle starts with the spreading centers. On the entire other side of the plate, we get to these subduction zones where they go back into the earth. They dive down underneath a lighter plate. And that means that, as we said before, that portion of the crust returns to the mantle. So the oldest crust that we have, for example, if we if we looked at the South American plate over here to the left, the youngest rocks on the South American plate are going to be at the mid-ocean ridges. The oldest rocks are going to be right over here near the subduction zone, because they've traveled all the way from the center, the mid-ocean ridge, all the way over to the descending parts of the mantle. So we know about subduction zones mainly because of seismic studies. We didn't know where the other parts of plate boundaries were until we started mapping out earthquakes. So a fun fact about these earthquake studies is we had those bathymetric maps that were created during the 50s. During the same time, we were doing a lot of underwater seismic studies during the 50s, mainly because of the Cold War. So at that time, both America and the Soviet Union were testing nuclear weapons. A nuclear blast creates a large seismic event that can be detected on seismographs. So we wanted to monitor where nuclear blasts were occurring, and which means they were testing new nuclear weapons. So we were mapping out all of these earthquakes. And what we found was that these earthquakes line up on certain boundaries. And all those earthquakes line up on plate boundaries, is what we just ended up discovering. So because of the Cold War, we know a lot more about the geology of the Earth, which is pretty interesting. But subduction zones, as the plate is being subducted beneath the other plate, it's breaking down, it's becoming less stable, so it's creating all these fractures that end up creating earthquakes. So we're able to map out those earthquakes based on the density and the depth of those earthquakes. So these studies were developed by a Japanese scientist and an American scientist, Wadati and Benioff, who figured out how subduction zones create different shapes. So these graphs are basically Wadati-Benioff zone graphs. The y-axis is the depth from the surface of the Earth. The x-axis is distance from the beginning of the subduction zone. So for the top one, for example, this is the Marianas Trench, where plates are subducting far, far beneath the ocean floor. So it has a very nice exponential curve where you get some very shallow subduction, and then all of a sudden it drops off. All of these black dots here are earthquakes, so that's them mapping out the general structure of the subducting slab. In the Curl arc, you have a lot more gentle curve and a lot less data, but it still goes just as deep. And then when you get to Peru on the western coast of South America, this is a very, very shallow slab. That's because Peru, the Andes in general, these are all forms from the Nazca plate going up against the South American plate. The Nazca plate is not as dense as other oceanic plates. So it's diving down, but it wants to come back up. So it's pushing up against the overriding plate. So it's constantly growing, making the Andes grow into the rest of South America. So eventually, as that plate kind of disappears, it'll probably keep rising and form a new, thicker plate, making the Andes such a much larger mountain feature. But as you can see, this subducting plate doesn't go any further than maybe 150 kilometers compared to like 300 to 350 kilometers on the other two. So this is a very, very shallow plate. So as we mentioned, what controls this angle of subduction? Mainly the buoyancy. So for example, for the Marianas Trench, it's a lot younger, it's a lot hotter, so sorry, it's less hotter, so it's a lot more destined to sink further into the deeper parts of the mantle. So older and colder means it's less buoyant. So the Nazca Plate, so older and colder is something that the Marianas Trench is going through. Younger and hotter is they're more buoyant. They want to float to the surface. That's what we're seeing in Peru. The Nazca Plate is a lot younger and it's a lot warmer, so it's more buoyant. We're also getting a lot of different forces that are interacting in this area of subduction. So as you can imagine, as that slab is being pulled into the center of the Earth, it's getting a lot of resistance from the asthenosphere. Remember the Oreo cookie model, the asthenosphere isn't a liquid, it's just a little more fluid, so it's still going to encounter resistance. There's not a lot of resistance in this area in the Marianas Trench. In Peru, in the Andes, there's a lot more resistance, so we have a lot less steep of a subduction angle. This is also going to be useful if you hear the text of that. So I think that's where we're going to end today. And we'll pick up with the rest of tectonics tomorrow. If anyone has any questions about this material, let me know. It's a lot of concepts to throw at you in one class session, but that's kind of the story of the winter session just because of how short it is. So if you have any questions, let me know. I'll be in the chat for a little bit for after class. Also, don't forget to submit your reading assessments. Your reading assessment 1. Reading assessment 2 has been fixed, but I changed the due date and extended it just because there were some problems with it. So I didn't think it would be fair to have you keep the same due date for that. Quiz 1 is going to be due tomorrow. And if you have any problems with that, if you need any help or any extensions, let me know. Otherwise, have a great day and I'll see you guys tomorrow.
Professor, you said assessments?